Nuclear fusion. Humans have been trying to achieve this type of reaction and put it into a useful, efficient form ever since nuclear fission was achieved. Fission is the easier method to nuclear energy, where atoms are split apart. However, fusion is when atoms are combined, and the energy yield can be up to 4 times greater per fuel mass used than fission. One of the methods to achieving fusion is through magnetic confinement, of which there are 3 experiments we will explore: the tokamak, the stellarator, and the reversed field pinch. The tokamak is the basis for most magnetic fusion experiments. It is the most developed and researched type of magnetic confinement. It was invented in the early 1950s by Soviet physicists Igor Tamm and Andrei Sakharov. The idea behind how magnetic fusion works using the tokamak is that fusion can be achieved by combining plasma at very hot temperatures. The tokamak confines this hot plasma into a toroidal shape, or donut shape, using magnetic fields. The donut shape was thought to be the most effective because plasma moves in a helical path when subject to a magnetic field.
The main advantage of the tokamak reactor is how simple and versatile it is. The relatively simple design allows for the tokamak to be built on both small and large scales, ranging from a 2 megawatt output to a 2000 megawatt output. In addition, the simple design allows for a variety of different modifications to be made. Throughout the history of fusion research, the tokamak has been the basis for which many other fusion reactors, such as the spherical tokamak and reversed field pinch, have been built on. Different modifications to the reactor can be made to make the fusion process more efficient. One of the main downsides to the tokamak reactor is the materials requirement of the interior walls. The continuous presence of high-energy plasma inside the tokamak reactor will lead to the erosion of most common materials. As a result, the materials requirement for the interior walls of the tokamak reactor are incredibly complex and expensive. Another downside of the tokamak reactor is the power required to continuously operate. An incredible amount of energy is required to heat the plasma and contain it using the strong magnets. Throughout the world, tokamak reactors are still in operation and will continue to operate. The International Thermonuclear Experimental Reactor, or ITER, is an international fusion research project that will take place in France and use the tokamak design. Construction began in 2010 and is planned to be finished in 2019, with operations beginning in 2020. The European Union, India, Russia, China, South Korea, Japan, and the United States are all contributing to the project. The current plans have ITER generating 500 megawatts of power in 5,000-second intervals. The demonstration power plant is planned to be the successor to ITER. Construction will begin in 2024 and it will be operational in 2033. It is planned to generate 2 gigawatts of power continuously.
The stellarator was invented by Lyman Spitzer in the early 1950s. It came around at about the same time as the tokamak, using the same basic idea, however lost popularity as the tokamak began to achieve better results. Spitzer took the toroidal shape of the tokamak and suggested extending the torus with straight sections to form a racetrack shape, and then twisting one end by 180 degrees to produce a figure 8-shaped device. The idea behind this design was to reduce turbulence and cancel out net forces by having the plasma particles travel in opposite directions relative to each other as they went around. This design, however, was found to be not perfect.
The physical shape of the coils creates a current that generates a magnetic field. The magnetic field generated by a stellarator is more stable than that created by a tokamak. In theory, a stellarator could then confine the plasma in the reactor vessel indefinitely. The shape also allows for higher density plasma and creates an intrinsic stability that the tokamak design lacks. One of the largest drawbacks of the stellarator's design causes plasma particles to leak out faster than a tokamak. This is because the stellarator lacks a direction of symmetry and the magnetic fields. However, experiments at UW-Madison have used external copper coils to restore this symmetry and decrease the rate of leakage. The complexity of the stellarator design also makes the parts incredibly difficult to manufacture. The University of Wisconsin-Madison designed the most successful stellarator experiment, the helically symmetric experiment HSX, which used quasi-symmetry to reduce transport. In 2010, the project was granted $10.7 million by the Department of Energy to continue the research. In Germany, another experimental fusion reactor, the Wendelstein 7X, will be completed in 2015. Both projects hope to be starting points for large commercial stellarator reactors for clean energy resources.
Reverse field pinch is a plasma containment configuration that varies from others in that its magnetic field lines reverse near the plasma edge. The field lines coil outwards from the central toroid and coil in the reverse direction near the edge. This allows for internal fields larger than those at the magnets, and thus plasma containment with a magnetic field that requires less energy than other configurations use.
The reverse field pinch possesses many advantages. As it requires a weaker magnetic field, one could save on the energy and resources needed to create a large magnetic field, such as superconducting magnets and electrical power. In addition, such devices tend to be very delicate and sensitive. Therefore, the absence of such mechanisms would render the reverse field pinch more hardy and durable. In addition, the RFP requires a close-fitting shell to stabilize the plasma, allowing it to withstand high-energy nuclear reactions which can have temperatures of up to 100 to 200 million degrees. But it also has its disadvantages. A weaker magnetic field reduces the amount of control the user has over the plasma, leading to increased instability. The plasma may attain a multiple helicity state in which different layers of the plasma resonate and behave uncontrollably in certain areas. This disequilibrium can also render the device prone to tearing mode, which is a state of instability in which the magnetic field lines are torn and reconnected in a field of lower magnetic energy, leading to undesirable weakening of the magnetic field. Due to such instabilities, the reverse pinch field can only be used on a small scale and is not ready for commercial use. Currently, research on the reverse field pinch is ongoing and is conducted by major organizations such as the European Commission and International Energy Agency. The two biggest RFP experiments, that is the reverse field experiment in Italy, which has been operational since 1992, and the Madison Symmetric Torus in the States, which has been around since 1988, are currently being utilized to study the phenomena involved with RFP, such as the creation of bursts of current, to confine the plasma and fuel injection into RFP devices. If one can successfully control the plasma, it can be put to practical use. For example, the reverse field pinch can potentially be used to regulate fuel in fusion reactors. The reverse pinch field can also be used for research. It is commonly used in the study of magnetic fusion energy and plasma science.
There is a saying in nuclear physics about fusion: fusion is always 20 years away. While this phrase is based in history, the promise of its benefits have proven too tantalizing for the scientific community to simply give up on. ITER, the international project to produce the world's largest and most productive fusion reactor, is currently paving the way for the field with a promise of 500 megawatts, 10 times its input power when it is completed by the year 2020. According to ITER's website, the demo project is already slated to begin work on a plant that can increase this to 2 to 4 gigawatts following ITER's success. This is to say nothing of the myriad of engineers working to create new, more efficient designs independent of ITER. Fusion's goal may be nearly unreachable, but that will never stop the work.